Welcome back to another episode of Second Career Pilot. Today we're tackling a topic that's absolutely fundamental for every pilot, especially if you're maybe newer to aviation. Really getting to grips with how your aircraft performs. It's not just about the basic mechanics of flight. It's about understanding what your specific airplane can and can't do, across the whole spectrum of conditions.
Yeah, definitely.
Think of it as unlocking a deeper understanding of your flying machine.
That's right. It's about moving beyond just the controls and developing an intuitive feel for what your aircraft is capable of and, crucially, where its limits lie.
Right.
The primary source for this knowledge is your pilot's operating handbook, the POH, or maybe the aircraft flight manual, the AFM.
Right, the POH or AFM, those are key.
They are. These documents are like your aircraft's secret performance decoder ring, if you will, packed with information about every phase of flight.
Well, a really important thing to keep in mind right from the start is that the way this performance data is presented, well, it isn't standardized across all aircraft manufacturers.
That can trip people up.
Yeah, you'll see tables crammed with numbers in some, lots of graphs in others, and the underlying data itself might be based on ideal conditions or maybe a specific pressure level, or even a calculation that takes temperature into account, like density altitude.
Exactly.
So being able to recognize these different formats and knowing how to make the necessary adjustments for the conditions you're actually flying in, that's absolutely essential for safe and smart flying.
Precisely. The manufacturer gives you the raw data, but your job as a pilot is to interpret it and, apply it to the real world. It's about understanding the why behind the numbers.
Okay. So where do we start? Maybe with the air itself.
Yeah.
Atmosphere.
Let's do it. The atmosphere. It's more than just what fills our lungs, right?
No.
It has a real tangible impact on how our aircraft behaves.
Right.
Absolutely. The atmosphere is a mixture of gases, mostly nitrogen, about 78%, 21% oxygen, and then 1% other stuff.
Okay.
What's key for us pilots is that it has mass and weight, and it exerts a force pressure that fundamentally affects our aircraft.
And most of the oxygen is lower down, right?
Yeah, fun fact. Almost all the oxygen we can use is below about 35,000 feet. Think of the atmosphere as this huge ocean of air we're flying through. Its properties directly influence our little submarine.
Huh. I like that. An ocean of air. And one of the big properties is atmospheric pressure. It's not just something we hear on the weather report, is it?
Not at all. Atmospheric pressure is, well, it's a cornerstone of aviation. Yes, it drives our weather patterns, sure. But it's also what allows our wings to generate lift. And it's the engine behind some of our most critical instruments, like the altimeter, airspeed indicator, and vertical speed indicator. It's the fundamental yardstick we use.
So it's really the baseline for a lot of things. And I remember learning about standard sea level pressure. Can you remind us of those key numbers? We hear them all the time.
Certainly. Imagine a perfectly average day at sea level. The weight of the atmosphere above us exerts a standard pressure.
Okay.
In aviation terms, we quantify this as 29.92 inches of mercury, often abbreviated as HG.
Right, 29.92.
Or 113.2 millibars, if you prefer metric. And this standard pressure is defined at a temperature of 59 degrees Fahrenheit or 15 degrees Celsius.
Okay, 15C.
You'll see these standard values pop up constantly in your flight training and your POH. They are the anchors for, well, a lot of our calculations.
Right, those are the ideal benchmarks. But the atmosphere is rarely ideal, is it? It changes with altitude and temperature. That's where these lapse rates come into play.
Exactly. To create a consistent reference, a model of a standard atmosphere was developed. This helps everyone from aircraft designers to air traffic controllers work with the same baseline.
Makes sense.
The standard temperature lapse rate tells us that, on average, the temperature decreases by about 3.5 degrees Fahrenheit, or 2 degrees Celsius, for every 1,000 feet we climb.
2 degrees C per 1,000 feet.
Up to around 36,000 feet. Above that, in the standard model, the temperature pretty much stays constant. We also have a standard pressure lapse rate. Pressure decreases by approximately 1 inch of mercury for every 1,000 feet of altitude gained, up to about 10,000 feet.
1 inch per 1,000 feet.
Roughly.
Yeah. And this whole standard model, the defined temperatures and pressures at different altitudes, that's the International Standard Atmosphere, or IS.
Yes, precisely. It's often called IS, or the ICAO Standard Atmosphere, established by the International Civil Aviation Organization as a worldwide standard.
Okay.
Now, here's a key insight. The real atmosphere almost never perfectly matches this standard.
Right, it's always changing.
Always. Any deviation in temperature or pressure from these standard lapse rates creates what we call non-standard conditions. And this is why your POH and AFM are so vital. They provide adjustments, usually in the form of performance charts, to help you figure out how your aircraft will perform when the actual atmosphere differs from the standard.
Okay, so the atmosphere is a dynamic beast and rarely follows the textbook. Got it.
Right.
Now let's talk about some of these core performance concepts and help us understand how our aircraft behaves in this non-standard air. Pressure altitude is a big one. What exactly does that tell us?
Okay, pressure altitude. Think of it as a standardized way to talk about altitude based purely on pressure. It's the height above a theoretical level where the atmospheric pressure is exactly 29.92 inches of mercury.
That magic number again.
That's it.
Yeah.
We call this level the standard datum plane, or SDP. Your aircraft's altimeter is basically a very sensitive barometer. When you set it to 29.92 Hg in the little Colesman window, it's showing you your height above this standard pressure level. That's your pressure altitude. So it's like setting all the world barometers to the same reading. Your altitude reading then becomes a standardized pressure height, which is crucial because, well, aircraft performance is highly sensitive to air pressure.
Got it. So it's about leveling the playing field by referencing everything back to that one standard pressure, 29.92. And why is pressure altitude so important for us as pilots?
It's fundamental for a couple of really important reasons. First, it's a primary input for figuring out how your aircraft will perform. Many of the performance charts in your POH are based on pressure altitude.
Right, you need it for the charts.
You do. And second, air traffic control uses pressure altitude to assign flight levels to aircraft flying above 18,000 feet. It ensures everyone at those higher altitudes is referencing the same pressure level, regardless of the local weather below.
Okay, that makes perfect sense for separation. Now, density altitude is another term that gets thrown around a lot, and it sounds a bit more complex. How does that differ from pressure altitude?
Density altitude. It builds upon pressure altitude. It's pressure altitude, but then we correct it for non-standard temperature.
Ah, the temperature correction.
Yes. Here's an insight. Density altitude is the altitude in the standard atmosphere that would have the same air density as the air you're currently flying in.
Okay, say that again. The altitude in standard air that has the same density.
As the actual air you're in. So even on a cool morning at a high-altitude airport, if the temperature is above standard for that pressure altitude, your plane might feel like it's at an even higher and hotter location.
Which affects performance.
Dramatically, especially takeoff roll.
So it's all about how dense the air is. And how does that affect the aircraft's performance?
Exactly. Air density is king for performance. A higher density altitude means the air is less dense, it's thinner.
Right.
Think of it like trying to row a boat in thick molasses versus water.
Good analogy.
Thinner air negatively impacts three key areas. Engine power, less air for combustion, especially in normally aspirated engines. Propeller efficiency, less dense air for the prop to bite into, reducing thrust. And wing lift, thinner air exerts less upward force on the wings.
Okay, power, thrust, lift, all reduced.
Correct. Conversely, a lower density altitude means denser air, which generally translates to improved performance in all these areas. Better climb, shorter takeoff roll.
So when we talk about our aircraft feeling like it's operating at a certain altitude, even if our altimeter doesn't read that number, we're talking about density altitude. It's the altitude the aircraft feels aerodynamically.
Precisely. That's the perfect way to put it. It's the performance altitude.
Okay, now let's break down how pressure, temperature, and even humidity contribute to air density and therefore density altitude.
Sure. Density is directly proportional to pressure. So if the pressure goes up, the density goes up, and vice versa, assuming temperature stays the same. Pretty straightforward.
Higher pressure, denser air. Got it.
However, density is inversely proportional to temperature. If the temperature goes up, the density goes down, and if the temperature goes down, the density goes up, assuming pressure remains constant.
Okay, so high pressure and low temperature mean denser air, good for performance. Low pressure and high temperature mean less dense air, not so good. What about humidity? I always thought humid air felt heavier, thicker.
Yeah, that's a really common misconception. Moist air is actually less dense than dry air.
Really? Less dense, yes.
It sounds backwards, but it's because water vapor molecules, HO, are lighter than the nitrogen and oxygen molecules that make up the majority of dry air.
Mm-hmm.
So when there's more water vapor displacing the heavier nitrogen and oxygen, the overall mixture becomes less dense. In conditions of high humidity, the air becomes less dense, leading to a higher density altitude and potentially reduced performance.
Wow. So high humidity hurts performance too.
It does, often less significantly than temperature or pressure, but it's a factor. So a high density altitude is often a result of a combination. High physical elevation, low atmospheric pressure, high temperature, and high humidity.
The worst combination.
Pretty much. Conversely, lower elevations, high pressure, low temperatures, and low humidity tend to result in a lower density altitude and better performance. Sea level on a cold, dry day. That's peak performance conditions.
That's a really helpful breakdown of the atmospheric influences and these crucial altitude concepts, pressure and density altitude. Now, let's shift our focus to how all this translates into how our aircraft actually performs during different parts of a flight. Let's start with straight and level flight. It might seem simple, but there's definitely more to it than just keeping the wings level, right?
Absolutely. Straight and level unaccelerated flight, that's the key phrase. Unaccelerated means your aircraft is in a state of equilibrium.
Equilibrium.
This means the upward force of lift generated by the wings precisely equals the downward force of the aircraft's weight, and the forward force of thrust produced by the engine exactly balances the backward force of total drag acting on the aircraft. Lift equals weight. Thrust equals drag.
Before force is in balance.
Exactly. So understanding drag is key to knowing how much thrust or power you need just to maintain level flight at any given airspeed.
And as we touched on earlier, drag isn't just one thing. There are different kinds of drag working against us.
Correct. We primarily focus on two main types: induced drag and parasite drag.
Okay. Induced drag.
Induced drag is basically a byproduct of generating lift. Think of it as the cost of doing business for the wing. It's more significant at lower speeds when the wing is working harder at a higher angle of attack to create lift.
Lower speeds, higher induced drag.
Got it. And the other is parasite drag. This is the resistance the air puts up against all the parts of the aircraft: the fuselage, the landing gear, the antennas, everything as it moves through the air. This type of drag becomes dominant at higher speeds.
Higher speeds, more parasite drag.
Right. What's fascinating here is how the power required from the engine changes with speed to overcome this total drag. For example, while parasite drag increases with the square of your speed,
Okay.
the power needed to overcome it goes up by the cube of the speed.
Wow, the cube. That's a huge increase.
It is. Conversely, at those higher speeds, induced drag decreases significantly. The maximum speed your aircraft can achieve in level flight is ultimately limited by the point where the power or thrust needed to overcome all that combined drag equals the maximum power or thrust your engine can produce at that altitude.
Okay, that makes sense. Now, let's think about going up. Climb performance is obviously critical, especially after takeoff.
Yeah.
What are the key ideas we need to understand there?
Climb performance is all about having excess energy. You're either using extra power from the engine more than what's needed just for level flight at that speed.
Surplus power.
Exactly. Or you're converting some of your kinetic energy, which is your airspeed, into potential energy, which is your altitude.
Trading speed for height.
Right. If your engine is producing more thrust than the total drag is creating at a given speed, that excess thrust can be used to climb. Alternatively, you can pull back on the controls, increase your angle of attack, and trade some of your speed for altitude, even with the same power setting, resulting in a steeper, though perhaps slower over the ground, climb.
And we often talk about two specific types of climb: maximum angle of climb and maximum rate of climb, VX and VY. What's the difference between them, and maybe in what situations would a pilot use each one?
Good question. Maximum angle of climb, often abbreviated as VX, is all about achieving the greatest increase in altitude over a given horizontal distance.
Steepest climb path.
Exactly. Think of it as the steepest possible climb path over the ground. This is particularly crucial right after takeoff when you need to clear obstacles like trees or power lines close to the runway end. Achieving VX requires maximum excess thrust.
Okay, VX for obstacle clearance. What about VY?
Maximum rate of climb, or VY, focuses on achieving the greatest increase in altitude in a given amount of time. This is the climb speed you'd typically use to reach your cruising altitude most efficiently, time-wise. VY is more about having maximum excess power available.
Getting high quickly.
You got it. Here's maybe a simple way to remember. VX is your get over the obstacle speed right after takeoff, while VY is your get to cruise altitude fast speed.
That's a great way to put it. VX for getting over things, VY for getting up there quick. How do things like the aircraft's weight and the altitude we're flying at affect our ability to climb? I assume they hurt it.
They definitely do. Weight has a very significant negative impact. If you add weight to the aircraft, it needs to fly at a higher angle of attack to generate enough lift at the same indicated airspeed and altitude.
Yeah.
This increased angle of attack increases both induced drag and parasite drag. This extra drag requires more thrust from the engine just to maintain level flight, leaving less reserve thrust or power available for climbing. Simple as that. Heavier plane, worse climb.
Makes sense. And altitude.
Similarly, as you climb to higher altitudes, the air becomes less dense, as we discussed.
Right. Density altitude goes up.
This thinner air reduces the power output of your engine, less oxygen for combustion, and also increases the true airspeed required to maintain the same indicated airspeed. Both factors reduce your available excess thrust and power. So your climb performance steadily decreases as you gain altitude.
It gets harder and harder to climb.
It does. You'll eventually reach a point where the steeds for maximum rate of climb, Vy, maximum angle of climb, Vx, and even your best level flight speeds all start to converge.
They all come together.
Yeah. The absolute ceiling is the theoretical altitude where you have literally zero excess power left. Your aircraft can only maintain steady level flight at one specific airspeed, resulting in a zero rate of climb. You just can't go any higher.
Okay, absolute ceiling, zero climb.
And then there's the service ceiling, which is maybe more practical. That's defined as the altitude where your aircraft can no longer climb at a rate greater than 100 feet per minute. Still climbing, but barely.
100 feet per minute. Okay, those are definitely important limits to keep in mind. Let's switch gears now and talk about how far and how long we can fly. Range and endurance. These might seem straightforward, but I know there are some interesting nuances involved.
Absolutely. Endurance is simply the ability of your aircraft to stay airborne for the longest possible time.
Max time aloft.
Exactly. This occurs when your engine is consuming fuel at its minimum rate, which corresponds to the minimum power required to maintain level flight. Think of it as sipping fuel as slowly as possible, usually at a fairly low airspeed. Useful for, say, holding patterns or search missions.
Okay, minimum fuel flow, max endurance. What about range?
Range, on the other hand, is the ability to travel the greatest distance on a given amount of fuel. Maximum range is typically achieved at the most efficient balance between your airspeed and your fuel consumption.
Getting the most miles per gallon, essentially.
Pretty much, yeah. This often occurs near the aircraft's maximum lift-to-drag ratio speed, or LDmax, that's the speed where the wing is most efficient, giving you the most glide for your effort, aerodynamically speaking. So for range, you're trying to cover the most ground for every drop of fuel, which usually means flying faster than you would for maximum endurance.
So for maximum endurance, we're just trying to stay up as long as possible, maybe circling, not necessarily going anywhere fast. And for maximum range, we're trying to squeeze every last mile out of our fuel tank to get to a destination.
Exactly. Now, factors like the aircraft's gross weight, the altitude you're flying at, and the configuration of the aircraft, things like whether your flaps or landing gear are extended, all have an impact on range.
How so?
Well, for instance, a heavier aircraft generally requires more power and therefore burns more fuel to maintain a given speed and altitude, which reduces your overall range. Simple physics.
Heavier equals less range.
Right. Altitude can have a more complex effect. At higher altitudes, the air is thinner, so you might experience less aerodynamic drag, which is good for efficiency.
Okay.
But you also have reduced engine power available due to the thinner air, and your engine might operate differently. So finding the optimal cruising altitude for range is key. Cruise control for pilots isn't just setting a speed, it's the technique of managing this, constantly making small adjustments to airspeed, altitude, and power settings to maintain the optimum specific range that's the nautical miles you can fly per pound or gallon of fuel.
Right, finding that sweet spot. And I've heard that the effect of headwinds and tailwinds on range isn't always as simple as just speeding up or slowing down relative to the air.
You're absolutely right. Our initial thought might be, okay, fly faster into a headwind to make up for the lost ground speed, and maybe slow down a bit with the tailwind to save fuel since the wind is helping us anyway.
Yeah, that seems logical.
And while that general idea holds true in many situations, it's not a universal rule, especially for maximizing range. The optimal strategy for maximizing range in windy conditions depends very much on the specific performance characteristics of your aircraft and the strength of the wind.
So, no simple rule of thumb.
Not really one that applies perfectly to every plane. Often you need to consult specific performance charts in your POH, sometimes called cruise control charts or range profiles, or use sophisticated flight planning software to determine the most fuel-efficient true airspeed to fly in the presence of a specific headwind or tailwind. It's more nuanced than it initially appears.
That's good to know. It's another area where just relying on intuition might lead you astray. Now, there's a concept I find particularly interesting, the region of reversed command. It sounds a bit counterintuitive, maybe even dangerous if you don't understand it. What exactly is going on there?
Yeah, the region of reversed command, sometimes called the backside of the power curve. It occurs at very low airspeeds, specifically below the airspeed required for maximum endurance, remember. That's the speed for minimum power required.
Okay, slow flight region.
Right. In this region, something unusual happens. To maintain a constant altitude, if you decrease your airspeed further, you actually need to increase the power setting.
Wait, slowdown requires more power.
To stay level, yes. Conversely, increasing airspeed back towards the minimum power speed requires a lower power setting. This is the opposite or reverse of what we normally experience in cruise flight, where speeding up requires more power. That's why it's called reversed command.
Okay, why does that happen?
It's because at these very low speeds, induced drag becomes incredibly dominant. As you slow down further, the angle of attack has to increase dramatically just to maintain lift, which causes induced drag to skyrocket. You need a lot more thrust, hence more power, just to overcome that massive drag, even though you're going slower.
Okay, induced drag takes over. So if you're flying very slowly, like on final approach, and you get a bit too slow, you actually have to add significant power just to stop descending or to stay at the same altitude. That sounds like a potentially tricky situation.
It absolutely can be if you're not aware of it or if you react improperly. This is particularly relevant during slow flight practice when you're deliberately flying near the stall.
Mm-hmm.
During the final approach phase for landing, especially if you're trying to make a power-on short field approach, and even sometimes during takeoff if you try to climb out of ground effect before reaching a safe climb speed like VX or VY.
Okay.
If you inadvertently let your airspeed decay too much in this region without simultaneously increasing power appropriately, you can quickly find yourself in a situation with a high rate of descent, potentially getting dangerously close to a stall, and you'll need a lot more power than you might expect just to arrest the descent, let alone establish a climb.
So it really emphasizes the need for precise airspeed control, especially at these lower speeds, and understanding the power relationship.
Exactly. Pitch for airspeed, power for altitude, that mantra is critical. But understanding how much power is needed, especially on the backside of the curve, is vital.
Definitely something to keep firmly in mind, especially during those critical low-speed phases of flight. Speaking of critical phases, let's move on to takeoff and landing performance. Statistically, as you know, these are the phases of flight with the highest incidence of accidents. So a solid understanding of the factors involved is absolutely essential for every pilot, new or experienced.
You're spot on. Takeoff and landing are fundamentally about managing acceleration and deceleration within the confines of a runway.
Right.
During takeoff, you're accelerating from a standstill to the speed where your wings generate enough lift to overcome weight and get you airborne. During landing, you're decelerating from your final approach speed, through touchdown, to a complete stop on the runway. The required runway length for these maneuvers is determined by several key factors.
Like what?
Well, your takeoff and landing speeds themselves, the rates at which your aircraft can accelerate and decelerate, which depends on thrust and braking effectiveness, and, of course, the condition of the runway surface itself.
And runway conditions can vary quite significantly, can't they? It's not always a perfectly paved, dry, level surface out there.
Exactly. The baseline performance data in your POH typically assumes a paved, level, smooth, and dry runway. That's the ideal.
The best case scenario.
Right. However, in the real world, runways can be made of concrete, asphalt, gravel, dirt, or even grass. Any surface that isn't hard and smooth will increase the ground roll during takeoff because the tires encounter more rolling resistance.
Mm-hmm.
Soft surfaces like grass or mud can cause the tires to sink in slightly, and any loose material or obstructions like slush, snow, or standing water will significantly reduce your acceleration.
And landings too, I assume.
Definitely. The effectiveness of your brakes during landing is heavily influenced by the runway surface. A wet or contaminated runway, snow, ice, even just water, will significantly reduce the friction coefficient between your tires and the ground, potentially leading to a much, much longer landing distance.
I also remember learning about runway gradient, the slope of the runway. How does that affect takeoff and landing distances? Does it make a big difference?
It can, yes. The gradient is simply the amount the runway's elevation changes over its length, usually expressed as a percentage. An upsloping runway will work against you during takeoff. You're essentially trying to accelerate uphill.
Takes longer.
It increases the distance you need to accelerate to take off speed. However, that same upslope can help you slow down during landing, potentially shortening your landing roll because gravity is helping you stop.
And downhill.
Conversely, a downsloping runway will aid your acceleration on takeoff, like rolling a ball downhill, leading to shorter takeoff distances. But it will make it harder to slow down during landing, thus increasing your required landing distance. You need to factor that in.
Makes sense. Uphill hurts takeoff, helps landing. Downhill helps takeoff, hurts landing.
You got it.
And then there's the very real danger of water on the runway and the phenomenon of hydroplaning. That sounds pretty serious.
It is indeed a serious hazard, especially for landing. Water on the runway significantly reduces tire friction and can severely impair your braking effectiveness and your directional control.
What exactly is hydroplaning?
Dynamic hydroplaning occurs when your tires encounter more water than the tread grooves can channel away. The tire essentially gets lifted up off the runway surface by a layer or wedge of water, completely separating the tire from the pavement.
So you're water skiing, basically.
Effectively, yes. When this happens, you have almost no direct contact with the ground, and your ability to brake or steer using rudder and differential braking can be almost completely lost until you slow down enough for the tires to regain contact.
Scary stuff. Is there a speed where it starts?
There is a minimum speed at which dynamic hydroplaning can begin, and it's related to your main gear tire pressure. A common rule of thumb, a rough estimate anyway, is 9 times the square root of your tire pressure in pounds per square inch, PSI.
9 times the square root of the tire pressure.
Yeah. So higher tire pressure means a higher potential hydroplaning speed, but the key takeaway is landing at higher than recommended touchdown speeds greatly increases your risk of hydroplaning if there's standing water.
So it's absolutely crucial to adhere to the recommended speeds, VREF, and to be fully aware of the runway conditions, wet, dry, contaminated before takeoff and landing. What are some of the other big factors that specifically affect takeoff performance? We mentioned density altitude already.
Right, density altitude is huge. But gross weight is another major one. A heavier aircraft needs to reach a higher liftoff speed.
Okay.
It has more mass to accelerate, which takes more time and distance, and it experiences increased drag from needing a higher angle of attack, plus more ground friction. All of those contribute to a significantly longer takeoff distance.
More weight, more runway needed. Simple.
Very much so. Wind is another critical factor. A headwind is your friend on takeoff.
How so?
It effectively decreases the ground speed you need to achieve your required liftoff airspeed. If your rotation speed is 60 knots airspeed and you have a 10-knot headwind, you only need to reach 50 knots ground speed to lift off. This significantly reduces your takeoff distance.
Makes a big difference.
It really does. On the other hand, a tailwind is your enemy. It will require you to reach higher ground speed before you can lift off, substantially increasing the distance you'll need. Always avoid tailwind takeoffs if possible, especially if runway length is limited.
Good advice. We already mentioned density altitude impacts takeoff speed and thrust.
Right. Higher density altitude means a greater true airspeed needed for takeoff and less thrust available from the engine. A hot, high, and humid day can really stretch out that takeoff roll. Always calculate your performance beforehand.
And for landing, it sounds like many of the same factors are at play, just kind of in reverse as we slow down.
Generally, yes. Gross weight, again, plays a significant role. A heavier aircraft carries more inertia and will require a higher landing speed. REF is often higher at higher weights, and thus a longer distance to dissipate that energy and come to a complete stop.
Heavier landing, longer roll.
Exactly. A tailwind on landing, just like on takeoff, is detrimental. It increases your ground speed at touchdown, which will also significantly increase your landing distance required. Avoid tailwind landings whenever feasible.
And density altitude.
Higher density altitudes mean you'll be landing at a higher true airspeed, even though your indicated airspeed on approach, VREF, might be the same as at sea level. That higher true airspeed translates to a higher ground speed at touchdown, potentially increasing the landing distance, although the braking effectiveness might not change quite as dramatically as engine thrust does on takeoff.
Okay. And speed control on landing.
Absolutely crucial. Just like with takeoff, adhering to the proper recommended landing speed, VREF, usually calculated based on stall speed plus some margin, is vital. Approaching too fast, adding extra knots for the wife and kids, will significantly increase your landing distance, float you down the runway, and put greater demands on your brakes, increasing the risk of overheating them or running off the end. Fly the numbers.
That example we sort of alluded to earlier about a pilot maybe making multiple errors leading to near runway excursion.
Mm,
It really brings home the critical importance of understanding all these performance factors: weight, wind, density, altitude, runway conditions, speed control, and making sound decisions in real time.
absolutely.
It sounds like a chain reaction of seemingly small mistakes or misjudgments can quickly escalate into a dangerous situation.
Exactly. Aviation safety often talks about the error chain. Each seemingly minor deviation from standard operating procedures, or a misunderstanding of the prevailing conditions, or maybe pressing on when you shouldn't, can compound the effects of other errors. It rapidly leads to a scenario where a safe outcome becomes increasingly unlikely. Good aeronautical decision-making, ADM, is all about recognizing these risks early, understanding the performance implications, and taking appropriate and timely action to break that chain.
Okay, we've covered the various phases of flight and the key factors that affect performance in each. Now, there's a whole alphabet soup of performance speeds that every pilot needs to be familiar with, the V speeds. Can you give us a quick rundown of what some of the most important ones mean? We see them on the airspeed indicator.
Absolutely. These defined airspeeds, the V speeds, are crucial for operating your aircraft safely and within its structural and performance limitations. Let's hit some key ones.
Good.
True airspeed, or TAS, isn't usually a V speed itself, but it's your actual speed through the air mass, important for flight planning. Indicated airspeed, IAS, is what you directly read on your airspeed indicator, without any corrections. That's what you fly by reference to mostly.
Okay, IAS is on the dial.
Then there's calibrated airspeed,
Yeah?
CAS, which corrects IAS for instrument and installation errors specific to your aircraft type. It's usually close to IAS at lower speeds.
Got it.
Equivalent airspeed, EAS, takes it a step further and corrects CAS for compressibility effects, which become significant at higher altitudes and speeds, usually not a big factor for most light aircraft.
Okay, maybe less critical for beginners. What about stall speeds?
Very critical. VS0 is the stall speed in the landing configuration, typically gear and full flaps down. It's the bottom of the white arc on your airspeed indicator.
VS0 landing config stall.
And VS1 is the stall speed in a specified clean configuration, usually gear and flaps up. It's the bottom of the green arc. Knowing these helps you maintain a safe margin above the stall.
Very important. What about climb speeds?
We talked about these. VY is your best rate of climb speed, giving you the most altitude gain per minute. Good for getting to cruise efficiently.
VY, best rate.
And VX is your best angle of climb speed, providing the steepest climb angle over a horizontal distance. Critical for obstacle clearance after takeoff. VX is usually slower than VY.
VX, best angle, got it. What about speeds related to gear and flaps?
Yes, VLE is the maximum landing gear extended speed, the fastest you can fly with the gear down. VLO is the maximum landing gear operating speed, the fastest you can be flying while you're actually retracting or extending the gear. Sometimes they're the same, sometimes VLO is lower.
Okay, check the POH for those. And flaps.
VFE is the maximum flap extended speed. This is the top of the white arc on the airspeed indicator, the maximum speed you can have full flaps deployed. There might be intermediate flap speeds too.
Top of the white arc, VFE. Makes sense.
Huh.
What about maneuvering speed, VA?
VA, maneuvering speed. This one's important but sometimes misunderstood. It's the maximum speed at which you can apply full and abrupt control inputs without risking structural damage from excessive G-loads. It's not a speed you should fly in turbulence necessarily, but rather a limit for control application. And importantly, VA decreases as weight decreases.
Decreases with lower weight. Okay.
Then we have VNO, the maximum structural cruising speed. This is the top of the green arc, bottom of the yellow arc. You should only exceed VNO in smooth air, and even then, only with caution.
Top of green, VNO.
And finally, VNE, the never exceed speed. That's the red line on your airspeed indicator. It's the absolute structural speed limit for the aircraft. Flying at or beyond VNE risks catastrophic structural failure. Don't ever go there.
Red line, VNE.
Hmm.
Never exceed. Got it loud and clear.
These speeds are all clearly defined in your aircraft's PHAK, and as we mentioned, are often indicated by specific color coding on your airspeed indicator. Know them for your aircraft.
That's a really helpful overview of those key performance speeds. Now, all the data we've been discussing, the effects of the atmosphere, density, altitude, the aircraft's weight, wind, and so on, the manufacturers compile all of this into the performance charts in our POH or AFM, right? How do we actually go about using these charts effectively? Because sometimes they look a bit intimidating.
They can seem that way at first, yeah. But yes, your AFMPOH is packed with charts and tables that allow you to predict, or at least estimate, your aircraft's takeoff, climb, cruise, and landing performance under a wide variety of conditions. It's really important to remember, though, that these charts are based on flight tests conducted with a brand new aircraft, usually flown by experienced test pilots, assuming average piloting skills for calculations, and a properly maintained airplane.
So they represent good conditions and good technique. Maybe add a buffer.
Adding a personal buffer, especially for takeoff and landing distances on shorter runways or in challenging conditions, is often a very prudent idea. Always, always pay close attention to the specific conditions and any notes or assumptions provided for each chart. You need to understand what baseline the manufacturer used when generating that data. Was it standard temperature? Did they assume a paved runway? What power setting?
Read the fine print.
Absolutely. These charts come in various formats. You'll see simple tables with columns and rows of data, graphs with lines and curves you have to follow, and sometimes combined charts or nomograms that allow you to account for multiple variables simultaneously by drawing lines across different scales.
Right, I've seen those complex ones.
Often, the data points won't exactly match your specific conditions. Maybe your temperature or weight falls between the lines in the chart. In that case, you'll need to use interpolation.
Interpolation.
Which is basically making an educated mathematical estimate to find a value that falls between the printed lines or data points on the chart. Usually, it involves finding the difference between two values on the chart and applying a proportional amount based on where your actual condition lies between them.
Okay, so it's a systematic process of taking the current or forecast conditions, finding the right chart for the phase of flight, carefully reading the notes, entering the chart with your variables, interpolating if necessary, and reading off the predicted performance number. Can you walk us through a couple of practical examples of how we might use some of these charts in flight planning, say for takeoff?
Certainly. Let's say you're planning a takeoff from Denver on a summer afternoon, hot and high.
Okay, high density altitude situation.
Exactly. The first thing you'll likely do is calculate your density altitude based on the airport's field elevation, the current ambient temperature reported by ATIS or METAR, and the current altimeter setting to find pressure altitude first.
Right, pressure altitude corrected for temperature.
Then, you'd turn to the takeoff performance section of your POH and find the appropriate takeoff distance chart or table for your aircraft model. There might be separate charts for short field versus normal takeoff.
Find the right chart.
You'll then need to enter that chart, usually starting with your calculated density altitude, or sometimes pressure altitude and temperature separately. Then you'll account for your aircraft's planned takeoff weight. Heavier needs more distance.
Better weight.
Then you'll factor in the reported wind conditions, specifically finding the headwind or tailwind component using maybe another chart first. Headwind reduces distance. Tailwind increases it significantly.
Factor in wind.
And finally, you might need to consider any obstacles you need to clear after takeoff. Some charts give you both ground roll distance and distance to clear a 50-foot obstacle. Following the lines or finding the values in the table, the chart will then provide you with an estimated ground roll distance and/or the total distance required to get airborne and clear that standard obstacle. You might also need to consult additional tables or notes in the POH to make adjustments based on the runway surface if it's not paved, like grass, which increases distance, or if the runway has a significant slope.
Wow, okay. It's a multi-step process, but essential for knowing if you have enough runway.
Absolutely essential. You must do these calculations before every takeoff, especially when conditions are non-standard or the runway is short.
Okay, so that's takeoff. What about when we're up cruising? How do we use the charts to manage our fuel and range effectively?
Good question. For cruise flight, you'll typically find cruise performance charts or tables in your POH. These provide information on your expected true airspeed, TAS, your fuel consumption rate, usually in gallons per hour or pounds per hour, and sometimes your estimated range and endurance. These charts are usually based on various pressure altitudes, different engine power settings, often indicated in RPM for fixed pitch props, or manifold pressure and RPM for constant speed props, and sometimes outside air temperature.
Lots of variables.
Yes. Some charts might even provide recommended fuel mixture settings like best power mixture for speed or best economy or lean of peak mixture for maximum range or endurance.
How do you use them typically?
So, for example, you might enter a cruise performance table with your planned cruising pressure altitude, say 8,000 feet, and your desired engine RPM setting, maybe 2,400 RPM. You might need to adjust for temperature. Then you read across the table or follow the lines on the graph to find your estimated true airspeed in knots and your estimated fuel flow in gallons per hour for that power setting and altitude.
Okay, gives you speed and fuel burn.
Exactly. Knowing your aircraft's usable fuel capacity, you can then calculate your estimated endurance, how long you can fly at that setting, and your potential no-wind range, how far you can travel. There are also often climb performance charts that will tell you approximately how much fuel you'll burn, how much time it will take, and how much distance you'll cover just climbing from your departure altitude to your desired cruising altitude under specific conditions. You need to factor that climb fuel into your total trip fuel calculation.
Right, don't forget the fuel used to climb.
Never forget to climb fuel.
And we also need to factor in things like crosswinds when we're planning our takeoffs and landings, not just headwinds or tailwinds. Do the performance charts help us figure out the crosswind component as well?
Yes, most POHs include a crosswind and headwind component chart, usually a graph. It looks like a quarter circle or half circle with wind angles and arcs for wind speed.
Okay, how does that work?
To use it, you need two pieces of information: the magnetic direction of the runway you'll be using, and the reported wind direction and velocity from the weather report. ATIS, AWIS, METAR.
Runway direction and wind. Got it.
You then find the angle difference between the wind direction and the runway heading. For example, if the runway is 36, meaning 360 degrees, and the wind is from 330 degrees at 15 knots, the angle difference is 30 degrees.
Okay, 30 degrees off the nose.
Right. You find that 30-degree line radiating from the center of the chart. Then you follow that line outwards until you intersect the arc representing the reported total wind velocity, in this case, 15 knots.
Find the intersection.
From that intersection point on the chart, you typically read straight down to the horizontal axis to find the headwind component, and straight across to the vertical axis to find the crosswind component.
Ah, okay. It breaks the wind down for you.
Exactly. This is absolutely crucial for determining if the crosswind component exceeds your aircraft's demonstrated crosswind limit, which is also listed in the POH. It's not necessarily a legal limit, but it's the maximum demonstrated in testing. It also helps you plan your approach and landing technique, like how much crab angle or wing low slip you might need to safely manage that crosswind.
Knowing the crosswind component is vital for safety.
Absolutely vital. Trying to land or take off in a crosswind stronger than the aircraft is certified for, or stronger than your personal capability, is asking for trouble.
It really sounds like these performance charts are the pilot's best friend, maybe after the checklist, when it comes to truly understanding what their aircraft is capable of in specific circumstances. Taking the time to learn how to interpret and use them correctly is clearly not just good practice, it's absolutely essential for safe and efficient flight operations.
Absolutely. I couldn't agree more. Understanding your aircraft's performance data, using those charts correctly, it isn't just about passing your checkride or a knowledge test. It's fundamentally about ensuring the safety of yourself, your passengers, anyone on the ground, and making well-informed, smart decisions every single time you take to the skies. Your POA AFM is an invaluable resource. It's not just shelf filler. Investing the time and effort to truly understand its performance sections, practice using those charts, maybe even run some scenarios on the ground that will undoubtedly make you a much more knowledgeable, more confident, and ultimately a safer pilot.
We've certainly covered a tremendous amount of ground today, haven't we? From the fundamental principles of how the atmosphere affects us through pressure and density altitude, the forces in flight, climb, cruise, range, that tricky region of reverse command.
Yeah.
All the way to the nitty-gritty of takeoff and landing factors and using those performance charts.
Yeah, it's a lot to digest, but it's all interconnected.
It really is. It's clear that there's a significant amount more to understanding how an aircraft performs than just, pointing it in the right direction and managing the throttle. Remember, always consult the specific documentation, the POH or AFM, for the exact aircraft you are flying for the most accurate performance data. Don't use generic numbers or charts from a similar model.
That's critical advice. Every aircraft, even of the same model, can have slight differences. Use the book for that specific serial number if possible, or at least the correct model's book. We sincerely hope this overview has provided you with a solid foundation for building your understanding of aircraft performance. It's really a journey of continuous learning in aviation.
It definitely is.
So keep exploring your POH, keep asking questions of your instructor, of other pilots, and keep refining your understanding through practice and experience.
What other questions do you listeners have about your aircraft capabilities? Are there any specific flight scenarios or maybe performance aspects you found confusing or would like us to explore in more detail in future discussions? Please do let us know.
Yeah, your feedback is incredibly valuable. It helps us tailor these discussions to the topics that are most relevant and helpful for you, especially if you're working through your training or just looking to brush up on your knowledge as a second career pilot.
Thanks for listening.